Yeah, all good? Cool. So apparently it's the 10th session of the pudding, so thanks for coming. I have to wear this t-shirt also apparently, but not my choice. Just kidding. So today we're going to see Groth16, so that's the GOAT of proof systems. Like the name says or indicates, it's invented in 2016 by Mr. Groth, Jens Groth. And for some reason, it's so good that people still use it today. So you'll see it in all sorts of applications. And even if people have moved to like more modern proof systems, they still wrap their proof systems with Groth16, or a lot of people do, because of reasons we're going to see. So Groth16, kind of old, like 10 years old, I guess. Who knows, it could be like today's, could be the birthday of Groth16, I don't know. And still very relevant. People still use it for reasons we're about to see. I've never really understood Groth16 in spite of being in the field for quite some years. And so that was my opportunity to sort of dig into Groth16. It's always, so I sort of wrote the equation that you get at the end. And I was always sort of puzzled. This is the verifier equation. If you, spoiler alert, I don't know if you can see well on the back, but the verifier equation here, and here's the CRS. So that's like the parameters, I guess, that the prover and the verifier are going to use. And if you didn't know, Groth16 is a zero-knowledge proof system, but I'm just going to assume everybody knows that. So my goal today is going to be to try and explain Groth16 in a way that I haven't seen before. I haven't really seen intuitive explanations. And I'm hoping that I can go from scratch to this thing in the end. I think it's going to be a bit rough, because this thing like packs a lot of stuff, but I'm going to try to do my best. And if I know some people know about Groth16 in the audience, so if you have questions or anything like that that can help me clarify what's happening, then we can do that. Cool. So the first thing I'm going to do is ask you guys, why is Groth16 cool? I was like, we can start with the interactive part, but tell me just like one property of Groth16, or like one reason you've heard Groth16 is cool, or how to define Groth16. All right. It's a game, so it's a quiz. Very small what? Very small proof size. We can even say that, so it's a succinct proof system, but it's more than succinct. I think succinct is like you have polylog proof size, but this one has constant size proofs and constant size. And I believe the normal instantiation, or the one we see the most, is BN254, the elliptic curve. And so it means that the proof is, I think, 128 bytes. So it's pretty far from all the other proof systems, especially proof systems that have like hundreds of kilobytes proofs. And the sort of reason why it's so small is that the proof is really just A, B, and C here. 3 elliptic curve group points. Anyway, anything else? All right, thanks. Anything else about Groth16?
Additions are free.
Additions are free. I guess so the arithmetization, I guess I'll talk about that next. We use R1CS, or Groth16 is used to prove R1CS, and in this arithmetization, additions are for free. I guess that's, yeah, we can say that. What else? What else? So I guess that's the good stuff, somewhat. Any downsides people can think about? All right, so trusted setup. So it's not transparent. You need to do that setup to obtain that common reference string. And not only you need to do a setup, it is circuit specific. And that kind of suck. Basically, every time you do this for a specific circuit, and if you have a bug in your circuit, or you did something wrong, or you want to update the circuit, whatever, you have to redo a trusted setup. And a trusted setup is basically, they do this whole like ceremony thing where they generate these things using a multi-party computation, usually, because these elements have to stay secret. So these are commitments. when you have those square brackets. And if they don't stay secret, then you can forge proof. So it's really bad, and that's why we call it toxic waste. And I guess that, yeah, I mean, that has happened a lot in the past. You see projects that have to do trusted setups over and over. I'm sure some people in this room might have done that in the past because of bugs or reasons. Okay, cool. Maybe I can stop here. I mean, verifier is succinct, verifier is efficient to run, and prover I think is quasi-linear, just because you have to do some FFTs, but so somewhat, very acceptable prover runtime, and verifier is fast, and proof size are very small, and that's why people love using it. And you see that on Ethereum or other chains like Aptos. People will end up verifying Groth16 proof. And it's relatively cheap compared to other proof systems. Cool, so we got that out of the way. Now I want to very briefly explain R1CS, so the arithmetization that we use. I have a session on arithmetization that I've done in the past. I think that was the first video that we've done in the pooling stuff. So if you want to learn about that, you can refer to the previous, so the first video. But very small recap. Imagine that you have a circuit, like some computation you want to prove. The first step is usually to understand how to create an arithmetic circuit, so a circuit where gates are additions and multiplications. And then you want to shape that arithmetic circuit in something called R1CS. I can never remember what it stands for, it doesn't matter. But essentially, you can see R1CS as like a table, 4 tables, let's say, so the same as like Plonkish arithmetization, air arithmetization, all of these things that people use to create circuits. I like to see things as tables, and the first table is only one column. I'm going to call it A, because that's what the paper names it, and that's pretty much a vector that contains, like you can imagine that this is the memory that the circuit is going to use, and it contains by convention, usually 1, the constant 1 here, then the public inputs, and then the witness. So you can imagine like temporary variables in your circuit will be stored at the end of this vector, and at the beginning you put 1 and then public inputs. So it's just like a memory region. You can think about it this way. And then, how should I call them? Let's say U, V, and W. We have 3 tables. They all have the same size. And when people talk about the size of the circuit, you can imagine that every row is like one, I call them R1CS gates. I don't think anybody calls them like that, but you can think about it this way. So every row is a gate, and then the bigger your circuit, the more gates you have. And finally, what this is going to look like is that you're gonna, how can I explain this? Oh yeah, I'll write the equation first, but what you're going to have to verify eventually is going to look like that. No, I always make this mistake. So that's the R1CS equation, I guess. Some people write it with matrices or like sums of elements. It doesn't matter too much. But essentially what is written here is a linear combination of any of the elements in the memory array, the witness. And UI is basically, let's say this is one gate. So this is the first row. And U0 is this guy here. Then you have U1, U2, U3, and etc. So you can set these to like 1 if you want to activate one of the entry in this array. You can set it to 0 if you want to like just cancel it. Or you can set it to like any numbers. And you can do the same on that side with like your VI. So here's the selectors that are going to activate some elements in that memory. And same thing on the right side. You can sort of see that as the output if you want. where you're going to activate by setting things here, 1, 0, I don't know. If you only want to activate this one, for example, we set that 1 to 1. Does that make any sense? I don't want to spend too much time with R1CS. I'm gonna run away from it after, but that's my very brief explanation of R1CS. All right, I'm gonna move on. I mean, I could take some examples. For example, if we wanted to add two things, if we wanted to, add this guy, this is a A1, let's say, with A2 plus A2 equals A3. Basically, we would set this one to 1 and everything to 0. Oh no, sorry. These two to 1 and everything else to 0 to activate these two in this addition. That's why addition is for free, by the way. And then there's no multiplication here. We just need a 1. So we activate the first one. So 1 times 1 here. And then here we would activate this guy here, the fourth one, to reach the index number 3. Right? So that's how you can do an addition, for example. And the reason why we have a 1 here is really so that we can add with constants. Or multiply with a constant, I guess. Cool. That's all I'm going to say about R1CS. And usually in Groth16, what they really look at is something called QAP, but that's the polynomial version of R1CS. So you can imagine that we can't really prove tables. That doesn't mean anything. So we're going to convert these guys to polynomials, and then we're going to prove a polynomial identity. Okay. So I'm going to talk about that next, and then I'll pause for questions. But this guy here basically is we're going to look at all these dudes here. We're going to pretend that these columns are the evaluations of a polynomial, U0x. So we pretend these are evaluations of a polynomial at some domain, and we interpolate that polynomial to get that what is that polynomial, and then we can rewrite this thing as this polynomial identity. And so you can imagine that this thing is going to be true for all x in some domain. I'll write domain because I think I'm going to use D after. So the domain could be like the point 0, 1, 2, 3, whatever. Doesn't matter too much. And we want this to be true, so you can imagine like here, if we take the first column here, maybe I should add the I here. If we take the first column here, and we evaluate to the first point in that domain, then we will check basically this selector times all of the witness times this selector times all of the witness, blah, blah, blah. All right. Does that make sense what I wrote here? For people that know about R1CS, I guess. And I'd say if that doesn't make sense, just pretend that this doesn't matter, and this is what we're gonna try to prove. Like it doesn't matter how we end up there. This is really the front end or the arithmetization part of Groth16, but eventually this is what we want to prove. And intuitively, here we do a multiplication. I'm just giving you some spoiler alert, but this is going to be like something like that times something like that. Like this is going to be an A and a B. The way usually proof system works is that we don't want to say like for all x. We want to say modulo that domain. And so the way we rewrite this is on the right-hand side, we say plus T of x times Q of x, which is basically, this is a quotient polynomial, and T of x is what they call vanishing polynomial, where the stuff vanishes over all the points of our domain. So, I don't know, imagine that the points are 0, 1, 2, like this is our domain, and we have only 3 rows. Then this is how we would construct the vanishing polynomial. And this thing you can easily see completely vanishes for x part of our rows, I guess, our domain. but take some other value elsewhere. So that's how we prove that this is 0, or this polynomial identity is true everywhere, is by vanishing it yeah, on this domain.
So it vanishes on indices 0, 1, and 2, or?
So this thing here is basically true only when x equals 0, 1, and 2. Or we want to enforce that. We want to prove that.
And what is that, x equals 0, 1, or 2 at all times? Or like what enforces the vanishingness of the polynomial always?
I guess it's a property of the polynomial. It's like if this polynomial has roots in 0, 1, and 2, then you can like divide it by such a polynomial. And you can see that as sort of a Euclidean division, where this is the quotient and this is the rest. And I guess this is one way of saying it. Cool. So okay, so doesn't matter how we end up here, really. It's just a recap. And if it's not, just ignore it too much. Don't think too much about it. But this is what we're going to try to prove. And we're sort of gonna, maybe I should delete that, erase that. So I have more space, because I'm gonna need the space. Up. We're sort of going to start somewhat naively by asking the prover to produce, like I said earlier, these. Right. And then you can imagine that the verifier at some point will check, like the prover will send something that looks like that and looks like that. I always make this mistake. It's horrible. And then the verifier will check, oh, is AB really equal to this sum plus T of x QX. Like we can call that the QAP check or something like that, but essentially we're gonna want to do something like that. And you can sort of see that in the end equation. Don't look too much at that, but this is what we're gonna try to do as the verifier. At this point, we're gonna want to take commitments. So how to end up there? So one of the tricks to make this like efficient is not to check this polynomial identity in the clear, but instead use the Schwartz-Zippel Lemma. I also don't want to talk too much about that. Schwartz-Zippel. But basically, if this is true, then it will be true on all the points, x, like everywhere, not just our domain. But if this is not true, this is mostly going to be, if you evaluate this equation at x, at some random point x, this is with high probability not gonna be, this part, the right-hand side is not gonna match the left-hand side. We're gonna get a different value here and a different value here. So that's what Schwartz-Zippel tells us. It's like you can quantify like what's the risk when you when you generate a random x and you check this equation, that if these two matches, that you were fooled by the prover, right? The risk is really these two are not supposed to match, but the prover was lucky or found a way to, for some random x, make this match with this. Highly unlikely. So this is, if you know any other proof system, this is the bread and butter of every proof system, basically. So if you know KZG, for example, or this kind of pairing-based systems, what they do instead of choosing x after the fact, so for example, Plonk or these kind of proof systems would sort of try and choose this evaluation point after the fact, but Groth16 sort of chooses it in advance during the setup. It's what makes it more efficient in a lot of ways. And so the way they do it is that during the setup, they will create a CRS that has a commitment to some value x, or like stuff evaluated at x, basically. And so when you look at this, what you will really be doing here is you will never know the evaluation at X itself, but you will compare commitments. You will check this identity within commitments. Like some people say hidden in the exponent. So anything that has an X in it will be hidden, basically. Commitment, you can think about that as if you have an elliptic curve and you have a generator G and you want to commit to like A, you'll do like A times G. And this is the commitments that they use here. So for example, during the trusted setup, they will generate some X that nobody knows using this multi-party computation, and they will multiply it with like some generator G, and they will get the commitment. They will get the commitment of X. And these are homomorphic commitments, so you can add them together, you can scale them and stuff like that. Actually, that's pretty important because that allows you to, if you have the powers of X, so let's write it like this. If you have 1, a commitment to 1, a commitment to X, a commitment to X squared, a commitment to X cubed, and etc., then you can actually produce this thing here, because the evaluation of your polynomial at X is just a linear combination of elements of your CRS. So, okay, I said a lot of things. Any questions at this point? This doesn't work, by the way. Just I'm trying to create something that will look like what we're going to do. But essentially, that's what I want to do. I want to check something, not in the clear, because we're checking that at a random evaluation X. And so that's part of the CRS. And we're going to ask the prover to give us elements, or like parts of that R1CS equation by taking linear combinations of the CRS. And then we're going to try to check if it fits, if the evaluation of these things is true within a commitment. Yeah. Does that sort of make sense? We want to check the same equation, but hidden in a commitment. And it's not a polynomial, it's really an evaluation here at some random X that nobody knows. All right, so that's the first step, and it's always hard to get to that step. I mean, if this is confusing, the rest is going to be very confusing. But the thing we can sort of notice here first is that we're doing a multiplication here and here as well, by the way, but here that involves commitments. And so eventually, like if as the verifier we want to do this, we're doing a multiplication of commitments. And so that's a big problem. Like we don't know how to do multiplication of commitments without elliptic curve pairings. And so I need to introduce elliptic curve pairings. And that's essentially why KZG or like Groth16 or these kind of schemes use pairings. Because at some point in their scheme, they want to do multiplication of commitments, and to do that, they need pairings. That's one of the only way, maybe the only way we know of doing that. Yeah, how else can we do multiplication of commitments? Interaction? Okay.
We need pairings if you want to. It's not it.
Right. Maybe there's some other, I don't know. Anyway, off topic. So what are pairings? I also don't want to talk too much about that. But so imagine that pairing is going to be something that we instantiate with a elliptic curve. So not all elliptic curves support pairings. And a pairing is basically something that allows us to do a multiplication of commitments. So the way people write it usually is like E of A and B. And essentially, what this looks like is, I don't know, behind A there's something, let's say A. A commitment, it's a commitment of A times a commitment of B. And what we get usually at the end is the result of the multiplication, but in this other group. And this group is also a curve, and usually this thing here is like in a target group, this guy here is in a group 1, and this guy here is in a group 2. So we choose different generators that on different curves that generate these groups, and magically we can, whatever we have in this side in this group and whatever we have in this side in this group, we can multiply, but it's not in the clear. We don't get A and B, A times B, but we get it hidden in the exponent again as a discrete logarithm. And maybe one more thing. Yeah, so this is, maybe let's separate that. Pairing, right? Maybe that we should do a session on pairings at some point. But one more thing I can say is that sometimes G1 is equals to G2. Actually, in Groth16, this doesn't matter if G1 is equal to G2. With the curve that we usually use, or that people tend to use with Groth16, it's the BN254 curve. These are separate. It's called a type 3 pairing. Doesn't matter too much. But Groth16 proves that this scheme is secure even when these two groups are the same. And so that's why here in my CRS, I didn't write exactly where these guys are in. Usually you would see something like 1 or 2 or 1 telling you where they are, in which group. But since we can sort of prove this in even when they're in the same group, I'm not going to care too much. And actually, every time I multiply stuff, I'm going to write it like this, but you have to imagine that we'll be doing a pairing. And I think that's all I can get away with. And I can stop here about pairings and move on. All right, any questions on that? Why these kind of things would be useful for us? Does that make sense? All right, so that out of the way, we can imagine that we'll be able to do A times B equals to this thing times this vanishing polynomial that we know as the verifier, because this is part of the circuit. This is based on the circuit size and the domain we chose. And Q of X is the quotient polynomial. Usually, in a lot of proof systems, it's about proving that this guy exists. And I guess here is going to be the same. Especially, you don't want to show that in the clear if you want ZK in your protocol. But I'm not going to explain Groth16 with ZK actually, but it's not too hard to understand why ZK works on top of it.
You wouldn't want to show it as a clear anyways, because it's not succinct.
Right. So there's always two reasons to take commitments. It's more compact, and it also hides stuff if you want ZK, somewhat. But yeah. Okay. What should I do now? So there's a lot of issues with this guy here, and that's why we're going to end up with this scheme there. And so I need to pick one of the issue and then go with it. So I'm gonna write it here, I guess. Let's do some cleaning. By the way, I gave the powers of X. This is what Groth16 do. They give you the powers of X. Here I could have given you the evaluation of UI at X directly in the trusted setup, but this is gonna be useful for later. So if you had the UI X for all I, you could do a linear combination like that. But if you have the powers of X, you would evaluate that as, if U0 of X is like C0 plus C1X plus C2X squared, then you would do C0 times 1, the commitment to 1, plus C1 times X plus C2 times X squared. And these are parts of the CRS, because they're in this guy. Right? I equal to 0 to like n. Maybe n minus 1. So anyway, that doesn't matter too much, but just a detail. So one thing that's annoying in this check that we're trying to do is that, and by the way, this could be this thing here, or maybe I should use different colors. All right, up. We could imagine this thing here to be like C, like another proof point. We're eventually not gonna, let me call it like E or something like that, because eventually we're gonna remove that. But you could imagine that this is another proof element. And so I'm given A, B, and E, and maybe like, maybe this guy is called like F. And then T of X I can compute myself as the verifier, and I do this multiplication plus E equals A times B, and I'm like, all right, that makes sense. I think that we verified what we wanted to verify. Unfortunately, it doesn't work. One of the reasons is that we don't know if A, B, and E in this example here have used the same AI. They could have used a different linear combination here, so a different witness, right? AI is our witness. And it's important that they use the same witness. Obviously, it's also important that they use the actual UI, which are the columns of the circuits, right? Remember, our circuit is uniquely defined with UI, VI, and WI. So we sort of have these two problems here. So the check we can do, and I guess we can call it the consistency check or like witness consistency check, is to do is to take a linear combination of these guys. In cryptography, when something doesn't work and you want to verify something, always take a linear combination. That's going to be my segue. So how to do that? Yeah, so if you have A, we're going to do beta times A plus alpha times B. I'm doing that because this is going to match the paper eventually. Plus, I called it E there. What do we have? We have something that looks like beta. Presumably, if these points were computed correctly, we have something that looks like AI UI X plus alpha AI VI X plus AI WI X. I'm going to move. Does that make sense? So if A and B and E were computed correctly, we get this, right? And one can notice that they can extract the AI, and we get that thing in the outside. Plus alpha VI. No. Does that make sense? By taking a linear combination, beta, alpha, and 1, I guess, we get presumably something that looks like this. So the individual parts of the R1CS equation. And then, since they all share the same AI, presumably, if things were done correctly, we can extract this AI here. And so that's what we want to verify. That's what the verifier is eventually going to want to do. They're going to do this thing here. And if it looks like something like that, then we're good. And they're going to go one step further, basically to enforce that it looks like something like that. They're going to put all of that inside a commitment. So the trusted setup is going to look more like that. So the trusted setup will produce these guys as part of the CRS. So you can see it appearing here and here except that here they're divided by delta and gamma, but we're going to ignore that for now. And you can see here it's for I smaller or equal to L. So these are the public inputs. I'm not going to explain the public inputs now. I'll explain that at the end, so you can ignore that guy first. And here you can see, or you can pretend that this guy and this guy are the same. So they're beta times ui plus alpha times vi plus w. And for all columns. And this linear combination in the CRS is sort of a commitment of your circuit. This is really what your circuit is about, right? The UI describes this part, the VI describes this part, the WI describes this part. So the fact that this appears in your CRS is really where the circuit is hard-coded inside the CRS. And by the way, this is one of the reasons, I mean, this is why it's a circuit-specific protocol. And this is also one of the reasons why it's so efficient, is because I guess you're hard-coding so many things in advance. Like, or in my mental model, it's like, wow, these things is so fast and so succinct. But I guess it's because we're putting so much of it in the CRS, within the CRS. So, okay, so we want to do this consistency check, where we get A, B, and E. And we want to check that it's equal to this thing. So how do we produce this as part of the prover? Well, this is just a linear combination of these guys. So what we can do is that we can ask the prover to produce this thing. And we actually are going to call this thing C. When I write it here, C. So this thing here is going to become a proof element. But we really want the prover to only construct C based on these guys here. Otherwise, if they construct C with like, maybe I should add to the CRS. We added, what else is in the CRS? We added alpha, we added beta, we added, yeah, so this, by the way, will be a commitment. We really don't want to learn these guys. So this is gonna be a commitment. You get the idea, sort of. Yeah. And we have also this new thing here. I'm not gonna write it down. But we want the prover to produce this thing here, only using these guys as part of the CRS, but not using the XI, not using alpha, not using beta. Otherwise, they're just gonna reproduce whatever is on the left side. So that doesn't make sense. Does that make sense what I'm saying here? So this is like fundamental, actually. This is like probably one of the most important things in Groth16, and the way they prove that this works is that whenever you produce proof elements as the prover, you're limited to take linear combinations of what's in the CRS. And the way I see that personally is that the CRS is just a bunch of Lego pieces. Lego? How do you say that? What's the correct way? Lego. So these are Lego pieces. And you're sort of the prover can assemble its own stuff and give it to you as A, B, or C, or E here.
And alpha and beta are toxic waste things in the CRS that you're not supposed to have access to after this setup. Right?
So you're not going to have access to this thing in the clear, but they're part of the CRS, so you can technically use them in your C. Right? So here we're going to introduce a trick. I call it splitting factors. Well, no, separating factors. That's a better name. Separating factors. And basically to force C to be produced with these guys, we're going to add, actually we're going to multiply C with some random value. That's hidden, so we don't know what it is. So let's add delta here. And when we produce these elements here, we're going to divide them by delta. We're going to multiply these guys with the inverse of delta. This means that if you want C to really be able to match whatever is here on the left, you're going to have elements in C that are multiplied by the inverse of delta, because otherwise you're going to have garbage multiplied by delta. So my delta here is what I call separating factor, because it separates these Lego pieces from the other Lego pieces. And as a prover, you can only play with the, let's call them the delta Lego pieces. And whatever you use in the neutral Lego pieces are not gonna do anything for you. So the first trick was first trick is to use pairings to do multiplication. The second trick is to do a random linear combination to extract the AI outside of it. The third trick is to enforce the shape of that check by adding this linear combination as part of the CRS. So that's what describes your circuit. And the final trick is to use this separating factor to like force the prover to only use that as part of C. Only these guys. So C is really a description of your witness and your circuit. That's what C is. If C decides to be 0, that's basically a bunch of zeros used as witness vector, right? If C decides to use like some like AI equals 1 for all I, then the witness vector is all ones, basically. So when they decide not to put one of these guys for some I, it means that the witness at this point is 0. It's a deliberate choice. So what I want, okay, any questions? I'm gonna do the merge after that, the magical merge. But does that consistency check make sense somewhat? Yeah.
I just noticed something, like in your CRS at the bottom, the very last element of it.
This element here?
Shouldn't there be a divided, like according to what you're writing up there, shouldn't there be divided by delta?
Yeah. So we're jumping ahead, but good catch. So eventually we're gonna want to add this guy here, but not yet.
It's in the E.
I said the E was only this stuff.
Oh, shoot.
Right? So we're not doing like the R1CS or QAP check here. We're only doing a consistency check, just making sure that the same AI is used across the A, B, and E. So we're not there. We haven't really solved that part yet, or this we haven't done this check yet. But a good catch on the. But you shouldn't look too much at this part anyway. we're not there yet. We have alpha, beta. We just introduced delta. We have the power of x, and this one are merged into like a single one for now. But we're starting to have a CRS that looks like the CRS in the end. Okay, so the next thing I'm going to want to do is like, okay, this check seems to work. So it's one check, and as the verifier, you have to do this check, but you also want to do this check. Maybe let's go back to this check here and mention that we also want the same trick here. We don't want the Q of x was f, right? We don't want the prover to like be able to do too many crazy things with this x. Especially, we don't want any polynomial of degree n-1, because this guy is supposed to be of degree n-2, I think. Degree n-1, degree n-1, degree n-1, degree n, because you have n roots. And so I think this guy is n-2. So you want to, not only you want to prove that this thing exists, but you also want to bound its degree. So I think it's degree n-2. Smaller or equal to n-2. So to do that, we're going to use the same trick. We're going to introduce in the CRS a new separator. I'm going to call it epsilon. And here I'm going to multiply this with epsilon. We have triple multiplication, that's going to be a problem. And then I'm going to also introduce the power of xi divided by epsilon. So now the prover can produce f, this part of the proof, which has to be a polynomial in x that is smaller, of degree smaller than n minus 2, or equal to n minus 2. And we enforce that with our new separating factor epsilon. Eventually that epsilon is going to become delta, but at this point we could be like, let's call it epsilon, and then we can realize, oh, but if we call it delta, it's the same. And we can also, of course, there's triple multiplication here, so the other trick here is to create a single dude here, and basically the element of your CRS here are going to be like this. So the power of xi times t of x. So you're producing basically this guy directly. And yeah, that's it. I don't know if that makes sense. But it looks exactly like what we have here, except we're using delta here. Does that make sense?
What happens if you don't enforce the degree bound?
If you don't enforce the degree bound, the attack is probably going to be hard since we still limit it to n. But the definition of this thing, in the definition of this thing, I guess Q has a degree n minus 2. If Q doesn't have degree n minus 2, then this thing might not be true, basically. So they might, I don't know. You can think of an attack, but it doesn't.
Certain degree bounds aren't important, right? Like, I thought a lot of people use like very large powers of tau, and then they use it for a smaller phase 2 setting. And so those, like, they're implicitly assuming that those extra powers of tau don't go.
Right, that is true. That is true in. So yeah, sometimes the CRS is like truncated because your circuit is smaller. And for some reason it's okay. I think, okay, I don't want to say like a bad thing because I'm being recorded right now. But I think if you really want to do this attack, you need like a very large degree, and so it's hard to mount. But yeah, I don't remember exactly. But according to the definition of this thing, this is the degree of Q, and so you want to limit it here. Right? We want to be clean. We can think about it later. So, okay. So now I'm going to do the merge. Any other questions, I guess, before I do the merge? So I'm going to merge this check with this check here. For that, I'm going to use a different color. All right, so wouldn't it be nice if we had just a single check as the verifier? And so one of the things here you can imagine is that E, which is this guy here, is presumably equal to the multiplication of A and B. This is sort of what we want to check, plus this guy here. So what we can do is that we can replace this guy with A times B. And the only thing we need to change here on the right-hand side of the equation is to add our guy here. So it's like F times epsilon. That's essentially what, like, how you merge these two things. Because now you're not only testing. So we got rid of this guy now. E doesn't exist anymore. Now you're just testing that A and B are consistent. So they use the same witness. They look like A is using UI. B is using VI because the alpha is in front, the beta is in front. And this thing here will look like WI of X. I mean this guy here, plus this guy here, which is what we wanted to check in this QAP check. All right? We're sort of separating that guy here. I mean, you can think about it, but this is this works. and then we can think of like steps that take us from here to this final equation, but these steps are pretty small. But the hard thing is to basically see these two things as two different checks, the QAP check that looks more like R1CS, the check we want to do, and this check to make sure that they all use the same AI and they all have the same shape, linear combination of the UI or VI and WI. And then you merge these two checks by noticing that the check on C is basically a check on AB. That multiplication here, A and B. They're all the same. Modulo that quotient polynomial, that vanishing polynomial. Okay, so 3 more steps to get to the final equation. Or any questions on this one?
I guess for X's earlier question around like the degree bound, if the equality of like A times B equals C kind of gets broken, what is the effect of that attack? Does that just mean that you can't verify anything through the proof system, or is it sort of?
I mean, an attack here, like if we want to like mess with the degree bound, or like if we're not doing something correctly, the attack is really that someone might be able to forge a proof. Like eventually, that's really what you want to avoid.
It's something like more global, like spillover on, I guess the three like group elements, or
The 3 what?
like the 3. I think A, B, and C are all group elements.
Yeah.
So those are never changed through an attack.
I mean, the way you would do an attack, so a proof is A, B, and C, I guess, A, B, and C. So the way you would do it is that you would try to add stuff into C, or but we're talking about the degree bound of this guy, right? So that's in F, technically, it's there. So you would produce an F that is shaped in a way that's not allowed, let's say, and you would magically make this left-hand side match the right-hand side, in spite of them not supposed to match. You know, they're not supposed to match the different things, but you're sort of correcting the error by having this degree of freedom that you're not supposed to have. But I don't know exactly how the attack would work here, or if there is even an attack, considering you only get like two more X's.
Yeah, but by the way, I'm not sure. Like I don't have the attack in my mind as well, but just strikes what you said. I think when you move from the big powers of tau to like the phase 2 to the circuit specific, I think that's when you introduce the degree bound, right? Because that's when you commit to like specific TX, and then you divide by the delta. So I think this is where you say, okay, this is going to be my degree.
I guess what I was saying is the proofer at some point uses the bare powers of calculus to compute.
But not for this.
But it does use it to compute the A and B.
Yeah, but just not for the element.
When you say powers of tau, you mean powers of X, right? In the original paper, right?
But they can't use it for the thing that is like times T of X.
No, I agree. Like there's two different sort of.
Anyway, let me finish that, and then because we're almost there. So if that makes any sense, then it's great, because all the steps from now are pretty small. So one thing you can realize is C and F are like, there's no reason to really separate them, because they're linear combinations of different elements. I mean, I don't have the best way to explain that, but F has to be a linear combination of this guy. C has to be a linear combination of I guess I only wrote it here, of this guy. And so they're not going to collide. Or if they collide, it's fine because we, like, whatever we get by just changing this guy to delta is going to be the same. Like, there's no other way to like change the result, basically. So we can use the same separating factor, is what I'm trying to say. And since we can use the same separating factor, we can just remove that f delta and just have the prover produce a C that contains that directly. So C will be, it's kind of annoying to write, but it will be this thing here, right? This linear combination of beta ui plus alpha vi plus wi divided by delta plus a linear combination of this guy here. Yeah, I'm not gonna write it because it's such a pain, but it's the vanishing polynomial t of x multiplied by the powers of x up to n minus 2, so you don't go through that degree, divided by delta, so that it gets cancelled here. So that's one of the step. And the other step is that we can notice that this thing here really looks like the multiplication of a, b if you had, if it looked like that. And these guys are basically the cross terms in that, I mean, yeah, in a way, they're cross terms in that multiplication, and then you get alpha times b here, right? Yeah. So eventually here you're gonna get that alpha times beta plus. So that's a pairing. Oh. So I guess it's kind of a simplification. Instead of computing these things yourself, you can just ask the prover to, let's call it A prime and B prime, to produce these proof points that already contain the alpha plus A, beta plus B, so that when you multiply them together, we get that equation we were checking as like cross terms plus alpha times beta. Does that make any sense what I'm saying? And so now we get the final equation. It's A times B equals that alpha plus beta. Okay, ignore this part here, plus C times delta. So ignore this part because that's how to enforce the public inputs. And I can explain that. But that's exactly the equation we're checking. And to go from the other way around, if you look at the proof, basically you can think about that as the alpha and the beta here on that side sort of enforces A and B to have an alpha and a beta as terms inside of them. The fact that you have a linear combination of these guys enforces A to be a linear combination of UI, B to be a linear combination of VI, using the same witness, and A times B to be a linear combination of WI, using the same witness. So everything sort of fits perfectly at the end. All right, and so final step is to, okay, how do you enforce public inputs? You can just enforce them as part of the verifier equation. So the verifier wants to enforce that A0 equals 1. As we've seen, this is convention, that all the first A1, A2, A3, whatever, are public inputs. And so they're going to split what can be a public input in the CRS with the gamma separating factor here. And so gamma is going to get inside the CRS. And initially, this guy that was in the CRS, or rather this guy, is going to be split into two things. One with the gamma separating factor, where I is in the public inputs, and one with a delta separating factor, with I is greater than the public inputs. So this is the witness part. And so the prover, when producing the C proof element, will only be able to use the witness parts of the circuit and not the public input part of the circuit. And that's why it looks like that. And then here we'll have a gamma like this and a delta like this. And this is it. This is Groth16. If I lost you at some point, that's normal, I guess. And hopefully this adds to the folklore of Groth16 is hard to understand. With one more explanation, that's hard to understand. And if you want to look at the paper, that's maybe it'll be easier to understand now. Cool. Is that it now? You can clap now.